So today the application to games is Liar's Dice, which is a really interesting game, and I'm also pretty bad at it because I'm terrible at lying. It's also called Perudo. I don't know if you've heard of it called that. And how it works is this. So every player rolls 5 fair 6-sided dice, and you can play with theoretically any number of players, although it gets a little crazy if you go higher than 7, say. But you can play with any number of players, 2 or higher. And everyone has their own set of 5 dice that they roll, and they can see their own, but they can't see anybody else's dice. The way that I play, ones are wild, so they can count as any number, but people also play without that. And everyone takes turns bidding on what they think is the total number of a particular value. So they could say, I think there's 4 1s or something, or I think there's 6 3s or whatever. So they take turns, and as it goes around the table, each person either has to bid a higher value. So if someone said that I think there's 3 4s, the next person could say, no, I think there's 4 4s, or I could say that there's 3 6s or something. So you can up the bid either like to a higher number or a higher number of those numbers. But if they don't think that, they can actually challenge the previous bid. So they could say, no, there are not, you're a liar. And then everyone reveals their dice and find out who's right. So if the person who challenged is right, then the person who made that bad bid is out of the game. And if the person who challenged is wrong, then they are out. So there's a risk in challenging. So it's kind of like a bit of a hidden information game because you know what you have on your dice and you're trying to maybe convince people of other things that are going on. So we'll start with just a theoretical situation where there's 7 players, so there's 35 dice in total. And then, of course, we can use the binomial distribution because the dice rolls are all independent with the same probability of success to figure out how many of a particular number there should be. So just let's for now consider 6s. Doesn't matter what we pick. The number of 6s in total, without looking at any of the dice, so once everybody's thrown their dice and they're still covered up, is binomial with 35 trials and probability of 1/3. Now 1/3 again is because a 6 counts as a 6, but so does a 1 because the 1s are wild. If you were playing without that rule, then it would just be the probability of 1/6. So that's pretty cool. And because we know the mean and variance of the binomial distribution, we can actually figure out the average and the variance of how many there are. So the expected number is going to be the parameters n times p. So 35 times 1/3, which is 11.667. And the variance we know for the binomial is n times p times 1 minus p. So that's 35 times 1/3 times 2/3, which is 7.7 repeated. And if we take the square root of that, then of course the standard deviation is 2.789. So that's kind of neat. That gives you a good sense of, on average, how many 6s there would be at the start of the game with no additional information. But you have information, right? You can see your own dice. And so suppose that you happen to have 2 6s, then the only randomness is going to come from the dice that you can't see. And you can see 5 of them, so there's 30 dice that you can't see. As well, so at that point, then we could think about the random variable being the number of 6s on the remaining 30 dice that you can't see. That's obviously still going to be binomial with 30 trials and probability of success 1/3. And then again, we could find the total expected number is going to be 2, the 2 that you have, plus x. So we want the expected value of 2 plus x, which is 2 plus the expected value of x by linearity of expectation. And so since the expected value of x is 30 times 1/3, then the total expected number of dice is actually 12. The 2 that you have, plus on average 10 of the ones that you can't see. And then for the variance, we want the variance of, again, 2 plus x, but the variance of 2 plus x is just the variance of x, because variance works that way, right? Like a plus bx or whatever. The constant term does not affect the variance. Variance is a measure of how spread out something is around its mean. So if you pick up the whole distribution and move it, it hasn't changed the spread at all. It's still the same variance as it was before, without having to add 2 to it or anything like that. So the variance of 2 plus x is just the variance of x, which is 30 times 1/3 times 2/3, or 6.6 repeated, with standard deviation of 2.582. So that's cool. That means, if you've got your 2 6s and you want to bid some 6s, we can think about what choices could we make? Like, what bids could we make that we can be reasonably confident that are not false, that there are at least that many 6s, so that if you bid them, either you won't get challenged, or if you do get challenged, you would actually win. Well, what we can do is basically calculate what the probability is of the of the event that there are at least k 6s. Well, for that, we know that you have 2 6s already, so we would need x, the number of 6s in the other people's dice, to be at least k minus 2. If you bid k, you have 2, so the rest of them have to contribute at least k minus 2. And since this is a discrete random variable, we could just write that as 1 minus the probability that x, the number of dice on these, number of 6s on these other dice, is less than or equal to k minus 3. So we can calculate that. It's just a binomial distribution. We'll take 1 minus the probability x is less than or equal to k minus 3 for different values of k. And here I have a nice little table that I calculated for each of those things. So this is maybe a little more decimal places than you need, but obviously here the smaller k is, the higher the probability is, right? You're 100% sure that there are at least 2 6s because you have 2. You can be 99.99995% sure that there are at least 3 6s total, meaning that there's at least 1 amongst the other 30 dice, and so on. So in particular, you could be 95% sure that there's at least 8 6s. So you could bid that very confidently, very, very unlikely that there wouldn't be that many. If you want to be a little riskier, there's a 50% chance that there's at least 12 6s, meaning, again, 10 among the 30. And if you're feeling super bold, you can be 25% sure that there's at least 14 6s. After a certain point, though, it gets a little bit scary to make higher bids because you're not sure. But remember, you can also use information about what other people have bid. So that's kind of but also people might be bluffing, so it's hard to know exactly what's going on. So that's how the game works probabilistically. And I want to just walk through a game that actually occurs in the movie Pirates of the Caribbean: Dead Man's Chest. I know sea shanties are real popular right now, so this is quite an old movie. But in that movie, the characters play this game, and we can analyze the probabilities of how that goes. So let's see what happens. I actually posted a link to a YouTube video of it. I'm not going to play it on the stream because I feel like I would get copyright struck or something, but you can click on that. I'll post this on Learn if you want to see it. So this is how the game goes. We start off, I'm going to try and not give away the punchline too soon. Okay, so the main character, whatever, Will Turner, bids 4 5s when he has 3 of his own 5s. So that's a pretty fair, likely to be true bid. We could actually calculate what the probability of him being correct is, because he's playing with 2 other players. So it's him, Davy Jones, and then Bootstrap Bill. The names don't matter. But the probability of him being right, that there are indeed at least 4 5s in the total, is just the probability that out of the 10 dice that he can't see, there's at least 1 5. Because remember, he has 3 of them, so he's saying, I bet there's at least 1 other among those other 10 dice. They're playing without wilds, so P is 1/6 here. And so the probability that this number of 5s among the other 10 dice, if we call that x, that's binomial with parameters 10 and 1/6, and the probability that that is at least 1 is just 1 minus the probability it's 0, which is 0.838. So pretty reasonably likely that he is correct, that there are at least 4 5s. The next player, Bootstrap Bill, raises the bid to 6 3s. Which doesn't really help Will Turner out that much. Maybe it tells him that he probably does not have a lot of 5s, because if he did, he would probably bid 5s more. And then Davy Jones bids 7 5s, so he makes a huge jump in the bid with 4 of his own. So at this point, we could actually calculate the probability of him being correct, and that would be the probability that the 10 dice that Davy Jones, can't see has at least 3 5s. Without any info, just doing the straight up calculation, that would be 0.225, which is pretty risky. But he actually has some information, because Will bid 4 5s, so he probably has more than the average number of 5s. So you can see how you kind of use the information that other people have bid. Although, of course, Will might not have been telling the truth. Davy Jones doesn't know that. So again, how that number is calculated there, that probability x is greater than or equal to 3. That would be what Davy Jones needs to have happen for his bid to be correct. Because he has 4, he needs at least 3 total amongst the other 10. and that number of 5s among the other 10 is that binomial random variable. So we calculate it as 1 minus, something that looks like a minus is actually an equal sign, sorry about that. We can take 1 minus the probability there are 0, 1, or 2 5s among the other 10 dice. So 0.225. Okay, pretty exciting. So now it is Will's turn again. So at this point in the game, he has to either bid higher or challenge. That's how the game works. And what he does in statistical terms, he makes the incorrect choice, but this is a movie, not a math class, to actually bid higher. So he bids 8 5s. So from his own perspective, he's got 3 5s, and the probability of in total there being less than 7, fewer than 7, it ends up being 0.93. So that's, again, calculated the similar way. The probability that he would be correct to challenge Davy Jones and say, no, I think you're wrong, would be 93%. But and the probability of him bidding 8 5s, is actually only 1.5%, very, very small. And if you like, you can verify that calculation using the same binomial distribution. So he of course does have the information that Davy bid 5, so he probably has more than average, so it's hard to tell exactly without any information, but it's pretty unlikely that there are actually 8 5s or more, and pretty likely that there are fewer than 7. But, it's a movie, so for the drama, he bids higher, and bids 8 5s. The crazy thing is that it turns out that there are exactly 7 5s total. So that's really unlikely, of course, to happen exactly, but that makes things really, really dramatic. That challenging would be incorrect because Davy Jones is right, and upping the bid is also incorrect because then he will get challenged. So it's a big, exciting moment that he bids 8 5s, and then as the audience, you know what's happening. But then luckily his dad saves him by making a statistically impossible bid and losing on purpose, and then Will doesn't lose his soul. So that's how the game kind of progresses, and it's neat to just sort of see how each player's perspective changes, and in terms of the likelihood of other dice showing the number that we want them to show. We have the beta distribution. So this is a really neat distribution, and it's a nice example of a sort of continuous distribution that we can model with the tools that we have. We don't actually talk specifically about the beta distribution in this course, but we have all the tools from section 8.1 that we need to be able to calculate and graph and draw information from this distribution. So if you remember back in week 5, we talked about using the Poisson regression model to predict the value of a count data. So like the number of people walking through the SLC or the number of lightning strikes or whatever, like a discrete thing that's a count of a number of things that have occurred. But often in regression, which is again like using characteristics to assign a numerical value to an object, often the thing we're trying to predict is not a count of something. And in fact, in some cases, maybe the thing that we're trying to predict is itself a probability. For example, in like an insurance contract context, you might want to be predicting the probability that someone will have a claim within the particular period. Or you might want to predict the probability that that the server capacity is overrun and that the game crashes if you're running a game, whatever. So lots of times the thing that we're trying to predict is itself a probability. So if we want to do that, we want to make sure that the thing we're predicting satisfies the same conditions as probabilities do. So probabilities are real numbers between 0 and 1. So the appropriate thing to use to predict a probability would not be any of the discrete random variables we talked about in chapter 5. It's definitely not categorical, definitely not numerical in that sense, but we would want a continuous distribution. And we would also want it to be bounded between 0 and 1. Regression is really great at just predicting a number for something, but we want to make sure that the thing we're predicting is bounded between 0 and 1 because the axioms of probability say probabilities have to be between 0 and 1. So one distribution that we can use is known as the beta distribution. It's actually not just one distribution, it's an entire kind of family of distributions, and it's governed by two parameters, alpha and beta. And its probability density function is given by the formula here. So little f of x, that's the probability density function, the PDF, is some constant c times x to the alpha minus 1, and then 1 minus x to the beta minus 1. And again, it's bounded between x going from 0 to 1. And c is just whatever the appropriate constant is that makes that function integrate to 1. And we know it must because that's what it takes to be a valid probability density function, right? The area underneath the curve, whatever shape that curve is, has to integrate to 1 for it to be a valid probability density function. So depending on the values of alpha and beta, we can calculate the value of that constant that makes it a valid probability density function. The other cool thing about the beta distribution is that it looks very different. It has lots of different shapes. So it doesn't just have kind of one way that it looks. We're used to kind of distributions that have like a characteristic look to them. But all of them are always bounded between 0 and 1. So we can have distributions that are symmetric, we can have them that are asymmetric, we can have like big, I'll show you a little example in a second, but the distribution can have many different shapes, but it's always going to satisfy what we need, which is it's a real number between 0 and 1. So let's think about how we could use this in a machine learning context. If you were trying to use an algorithm to predict a probability and you had no prior knowledge of what it should be, you had no idea, you would probably start off with a really boring version of the beta distribution, which is where alpha and beta are both equal to 1. So think about what happens if you plug alpha and beta equal to 1 into this formula. We'll get c times x to the 0, well, that's 1, times 1 minus x to the 0, which is also 1. So we'll get f of x equals c, a constant. And if we want that function to integrate to 1, over the range from x goes from 0 to 1, the value of the constant c must be 1. So we get the world's most boring distribution, which you'll learn about, I think, in section 8.2, which is the uniform distribution on 0, 1. So it's a really boring distribution. It's basically saying we have no idea. The probability could be literally anything between 0 and 1. We have no information about whether certain values are more or less likely than any others. But if you had more data, more information about this probability, so let's say you observed a bunch of trials and saw the number of successes that occurred, or you observed a bunch of insurance policies and saw how many of them had claims, or you observed a bunch of days with this game running and saw how many times the server load was over a certain capacity, whatever. You can observe that and use that information to get a better estimate of what that probability might be. And you would change the values of alpha and beta according to that additional data that you find. So that's how we would use it in that machine learning context. Finally, I just want to look at a specific example. So let's imagine that we have set alpha and beta both equal to 2, just for fun. Doesn't matter, we can pick any values we like. We want to find the constant c that we need to make it a valid probability density function, and then just as well, let's see what it looks like, graph the probability density function. So again, if we have alpha and beta both equal to 2, then the probability density function, little f of x, becomes c times x times 1 minus x, for x between 0 and 1. Again, that's just subbing in alpha and beta equal to 2. Since the exponents are alpha minus 1 and beta minus 1, that just gets us this value here. So again, if we want this to be a valid probability density function, then we have to make sure that the area underneath the curve integrates to 1. So we want to integrate from 0 to 1 of this probability density function and set it equal to 1. So we'll do that. We'll say c times x times 1 minus x dx, integrated from 0 to 1. We can pull the constant outside because it's a constant. And then we can also just multiply through. So x times 1 minus x is the same as x minus x squared. Cool. And then integrating that is, again, pretty easy. So the integral of x dx is x squared over 2. And the integral of x squared dx is x cubed over 3. And so we can do that there. We get x squared over 2 minus x cubed over 3, all evaluated at both 0 and 1. And when we put those in, we get, I guess, 1/2 minus 1/3, and then minus 0. So altogether, that gives us 1 over 6 for what's in the brackets, so c over 6 in total. And so if we want that to equal 1, we have to set c equal to 6. So this kind of thing, where you're sort of taking a probability density function with a constant in it and finding the constant that we need to make it integrate to 1, is a very common kind of question that's asked in terms of section 8.1. So you may have to do that on your quiz 4 if you haven't taken it yet. The other thing we can do is look at the graph. So now that we know this function is 6x times 1 minus x, we can see what that looks like for different values of x. We can plug in any value we like of x. We can think about it, okay, if x is very close to 0 or very close to 1, then this function is going to be very small because right? If x is very close to 0 or very close to 1, there's a factor there that's very close to 0. It's going to be maximized actually in the middle. And the value in the middle, when x is 0.5, is going to be 6 times 0.5 times 1 minus 0.5, which is 6 over 4, which is 1.5, I think. So we'll end up with kind of a curve that looks like this. And in fact, I actually graphed it, and it looks like that. Pretty cool, kind of a nice little function. So this is saying if we have this beta distribution with alpha and beta both equal to 2, it's more likely to be a value near 0.5, less likely to be far away from it on either side, and it's a symmetric distribution. So it's kind of like the distance from from 0.5 has the same probability. You can also just play around with different values of alpha and beta and see how the shape changes. And there's a really cool cool website there. It's not secure. It doesn't have an HTTPS version, so you may not be able to access it depending on your security settings. But it's really, really cool. You can sort of slide these little sliders around to see the different shapes of the beta distribution. And if anyone asks me, I can show you that later on in today's stream. But that is it for the beta distribution and for the machine learning idea of the week. Just in case anyone is watching or watching this later, we did just release the marks for the midterm, and the solutions are posted as well. So if anyone would like me to go over those, I can absolutely do that. The marks are coming to you in sort of two different ways. Eventually we'll put them together and add them together for you, but for now we're confident that you can take two numbers and add them together. I hope you can manage that. The Mobius Part 1 grades will be coming to you through Mobius, so you can see how you did on each question. If you have a question about it, if you want to remark, follow the procedure that's posted on Learn. You email Divya with your name and ID number and all of that information about what question you want regraded. We're human. It's of course possible that there's a mistake, but so do that if you think there's a problem with your Mobius Part 1 grades. For Part 2, you will have gotten an email from Crowdmark with your graded paper. And you should have also gotten a feedback from Mobius as well, without a grade, because the grade on Mobius Part 2 is completely meaningless. But you should be able to see whether your specific numerical answers were right or wrong for your particular set of parameters for the questions. So I also posted the solutions to one set of parameters for the questions. Obviously, your answers will not be the same. Everyone has a different set of numbers. So that's why we wanted to give you the feedback through Mobius as well, because that will have the correct numbers, numerical values for each of the parts for your specific question. But the process for how you solve the questions is the same for everybody. So those solutions are posted. Have a look at them. And if you have questions about how your Part 2 was marked, after you have read the solutions and after you have read the comments on Crowdmark from the TAs about where and whether you lost any marks, if you still have questions, then you would email Divya, same thing, with your name, ID number, which part, which question that you have questions about, and why you think it should be different. So, I wanted to mention, of course, how to calculate your grade. As mentioned before, Part 1 was worth 30 marks and Part 2 was also worth 30 marks. So you just take the mark you got on Mobius Part 1, but make it out of 30. So if you got, a 90, then that would be a 27. And then you take the mark you got on Crowdmark, which is out of 30 as well, although some people have up to 32 if they got the bonus. And you take those two numbers and you add them together. And that's your midterm score, and it's out of 60. So again, if you're not sure how to do that, we will be eventually creating a grade item in Learn that's your total sum of the two components once we've figured out taken care of all the remark requests. But until then, you can add two numbers yourself. Oh, the average, I'm sure someone was wondering about that, was great. It was really, really nice. You did very well. Overall average was 81, I believe, on the entire thing, with a slightly higher average on the Mobius part and a slightly lower average on the Crowdmark part. So it also depends if you count all the zeros. So when you get, if you count everybody who didn't write the midterm at all in the average, that drags it down. So if I'm taking the average only of people who actually wrote the midterm, then it's about 81 overall, which is great. I'm really proud of everyone. Yeah, why not? I'll go over the solutions to the midterm, and hopefully that will be useful. So yeah, good. You can see that. So first question was about precipitation versus temperature. And you're given 3 numbers: the percentage of days that have precipitation, which is rain or snow, the percent of days that are below freezing, and the percent of days that are above freezing with no precipitation. And you're asked to figure out, first of all, what's the probability that the day has both precipitation and is freezing. That's what it means to have snow. So essentially what you have here is a situation where you have 2 events, precipitation and temperature, and you're given 3 out of the 4 possible numbers in terms of like how they can interact. So the easiest way, honestly, to solve this is to draw a Venn diagram, and I saw lots of people doing that on Crowdmark, which was great. You didn't have to draw a Venn diagram to get full marks, but it's a really good way to approach this type of problem. So start by drawing a diagram. And then we have the information that we are given. So we define some events, A and B, and we're told that P of A is one number, P of B is another number, and the probability of A complement intersect B complement, or equivalently, A union B with a complement over the whole thing, is that third number. So when you put that onto a Venn diagram, it kind of looks like this diagram here. And what we're looking for is the probability of both, the intersection A, B, A intersect B, A and B, whatever, same thing. So we call that X. And then we can see that here on this diagram, if we want to sort of carve up this sample space into 4 regions that are non-overlapping, we have to have like A without B, so A intersect B complement. That's going to be the first number minus X. And then on the other side, we have B without A, so A complement intersect B. That's going to be the second number minus X. And then the middle part is X, and then the outside both of those 2 events is our third number. And then solving for X, with this particular selection of numbers, you get 0.05. Your set of numbers will be different, and you can check the actual numerical value. If you didn't get it right, you can check what it should be by looking at the feedback on Mobius for part 2. So hopefully that makes sense. Please let me know if there's any questions so far. Second, we want to answer the question, are these events independent? And then also explain why. So a mistake that not a lot of people made, but a couple people made in the first part was to just say, oh, well, if we want the probability of both A and B, we'll just take the probability of A and multiply it by the probability of B. The problem is you can only do that if you know the events are independent. And we haven't said whether they are or not. But we have given you this extra piece of information, this like probability of neither of the events. And so this part B was supposed to be a little bit of a hint that if you had just used independence in the first part, maybe you should think about whether you can actually use it. So the way to do this, there's a few different ways you could do it, but the easiest way is to just say, well, if they were independent, then the probability of the intersection would be the product of the probabilities, and it's not equal to the answer you got in A, so obviously they're not independent. So that's, we're looking for kind of a logical explanation and a mathematical explanation and just a yes or no. So if you had all those 3 things, then you get 3 marks. Next, we have the probability that we're asking for is now conditional. So we can see here, given that a randomly selected day in March does not have snow, what is the probability the temperature is below freezing? So the word given there is telling you that this is a conditional probability. So you know that's kind of like setting off the alarm bells in your head that this has got to be conditional. If you see the word given, that's a surefire way to know that's a conditional probability. So we're basically saying, if we know that we do not have snow, what's the probability that the temperature is below freezing? And in terms of the events we've defined, the probability of no snow is just, well, the probability of A intersect B, which is snow, with a complement over that whole thing. And that's just 1 minus the probability of snow, right? That's fairly easy. So whatever you calculated in part A, 1 minus that is the probability of not having snow. The other one's a little trickier because we want to think what would it take to be below freezing and not have snow? The only way for that to happen is if it's below freezing and no precipitation, right? Because of the way we've defined the events, if it's freezing and precipitation, that's snow by definition. You're given that at the beginning. And so in order to be below freezing and no snow, it has to be below freezing and no precipitation. And using the Venn diagram, which is hidden under my head here, that you can find that that's just whatever your second number was minus whatever you calculated in part A. So again, double check the numbers for your individual question. And then of course we want the conditional. So we want the probability of both no snow and below freezing divided by the probability of no snow. That's the definition of conditional probability. And so we take those two numbers that we calculated, divide one by the other, and we end up with this number here. Again, it's going to be different for everyone. And a Venn diagram can be really helpful for looking at that. Basically, it's the probability of the right chunk, the semicircle on the right, divided by the probability of everything except for the intersection. That's what we're looking for. Lastly, for this part, we have, suppose two independent days are selected. Here you see the magic word independent, so you can assume independence of the days from each other. What's the probability at least one of them has rain, which we've again defined for you as precipitation and temperature above freezing. So to do that, we want to think about on a single day, what's the probability of rain? And that, again, by the way we've defined things, would be A intersect B complement, so precipitation and not below freezing. And that, based on your Venn diagram, is, I guess, the first number minus whatever you calculated in part A. And that's for a single day. So then for at least one of 2 days having rain, the easiest way to do that would be 1 minus the probability of not having rain squared. So that gives us this. So next, question 2. Audrey and Diana are playing a card game. The deck has a number of cards, of which 4 are special in some way. And in each round, the cards are split evenly between the 2 players. So we did have a few people asking, like, how many cards does each person get? And if you have a number of cards and they're split evenly between 2 players, that means each player gets exactly half the cards. That may have caused a bit of confusion, but just make sure you're reading questions carefully because that information was all given. So for the first part, we're going to let x1 be the number of those special cards dealt to one of the players, and find the probability function of that variable. And there's a few different ways to do this, right? You could just sort of do it by, first principles, one at a time. Say, okay, what's the probability that the first player gets none? Well, that means all of them have to go to the second player, so that's going to be 4 choose 13 divided by 26 choose 13, and you could sort of figure it out for each one. Or you could recognize that this exactly fits the definition of a hypergeometric random variable. The total number of objects is the number of cards in the deck. The number of successes is 4, the number of special cards. And the number selected by the first player is half of the deck. So, and we're selecting without replacement. We don't care about the order, and we're counting up the number of those special cards that person has. So it exactly fits the definition of the hypergeometric. So that was also a perfectly good way to do it. You could do it, again, by first principles, getting each value, or using a formula. We would have accepted either one of these, like a table or a formula or both, whatever would have been great. So that gives us part A. Part B is a little trickier. So we're going to let x2 be the number of those special cards dealt to the other player. And we want to find the probability function not of x2, because it's obviously going to be the same as the probability function of x1, but a new variable y, which is the difference between the number of special cards that each player has. So formally, the absolute value of x2 minus x1. Basically, what we're looking at here is how many ways can they be split, right? Can they be evenly split, or one person has all of them and the other person has all of them, or they could be 1 and 3 or 3 and 1. So there's only 3 possible values for y. So that was kind of the main thing that we were looking at in this part. We have this function, and the possible values for y are only 0, 2, or 4. That's the only way, because all of the cards are always dealt out. And you can find the probability function of y just using what we know about x1's distribution, right? Having it evenly split means that the first player got 2. Having it the difference between the number being 2, meaning it's 1 and 3 or 3 and 1, is just the probability of the first player getting 1 or 3. And since those are mutually exclusive, we can just sum them. And similarly for 4, we could have the first player getting 0 or 4, and that would both satisfy y equaling 4. So that was how we would obtain this value here. And then for part C, you wanted to plot the CDF of y. In this one, we were looking for a few different things. Obviously, the CDF you get by taking the probability function and kind of stacking it on top of each other. So the value at y equals 0 is obviously whatever you calculated in part B. So in this example, 0.407. The value at 4 is obviously 1 because 4 is the maximum. And for a discrete random variable, the CDF is equal to 1 at the maximum and beyond. And then for 2, it would just be the sum of the probability of y equaling 0 plus y equaling 2. And then for the graph, again, we're looking for making sure that it looks something like this. It didn't have to be as perfectly detailed as this, but it should be a step function. So you shouldn't be connecting the lines like on a diagonal or anything. You should have it be equal to 0 before y is equal to 0, because remember the CDF is defined for all real values of x. And once it gets to 4, it should be 1, and then it should stay at 1 forever off into the limit. So if your function looked mostly like this, then you probably did fine. There was, I think, a half mark taken off if you didn't have it defined at 0 and before 0, and if it wasn't a step function, and if some of the values were incorrect. But most people seem to be doing reasonably well on that graph. And then for part D here, we're saying that the players play 8 rounds of the game, and we're looking for the probability of some event. So for some people it was that all of the special cards go to one player. Sometimes it was that the jokers or the special cards will never be equally distributed between them. And I think some people had that it was each person has at least 1. So basically that nobody has 0. So whatever the event was, you would use what you calculated before in terms of the probability function of y, and then take the probability of that being satisfied and raise it to the power of 8, because the rounds are independent. So that gives you this value here. And then the cool thing was thinking about what will happen to that probability if we increase the number of rounds to be very large. So what you can do, again, you didn't have to answer it exactly the same way as we did here in the solutions, but because you're playing this game under identical conditions, from the relative frequency definition, we would expect that about that appropriate percentage of the time, it would satisfy it, and the rest of the time it wouldn't. So if we repeated the experiment over and over and over again with that relative frequency definition, eventually there will be a time when the two players have the same number or don't have at least one, or whatever the situation was for your question. So as we increase the number of rounds, the probability of never having one particular thing happen that has a positive probability of happening is going to go to 0. So here, this is sort of a classic combining models problem. There's sort of a million of these in the course notes. They're all very similar. And in this one, we have someone working at home and counting trucks that pass their house, and certain percentages of them are from different companies, so FedEx, UPS, and other. First of all, we wanted to think about the assumptions of the Poisson process. I always ask this to think about critically evaluating whether the assumptions for the Poisson process would actually hold in this situation in real life. So you didn't have to agree with yes or no for any of the conditions. You could make an argument for each of those conditions that the answer should be yes or that the answer should be no. What we were looking for, and we've told you this before, is whether you've thought about what those conditions would mean in this context and whether they would actually hold or not. So you can't just say, yes, they would because you told me to use a Poisson process. We want you to think about, would they actually hold in real life? So you could make an argument again either way. Independence, maybe they run on a schedule. So if you just saw a UPS truck, maybe there isn't likely to be another one after that. Or maybe it probably is independent within reason, because who knows. Homogeneity, there probably are higher rates at certain times than other times. But you could also say that in this example, we're talking between 8 a.m. and 4 p.m. And in that time, maybe it is reasonable that the rate is constant. Individuality is probably always going to hold, unless it was like a truck that was towing another truck. Then individuality is pretty much individuality almost always holds, unless there's something that would cause two events to happen at the exact same instance. So just for any question like this, we're not looking for a yes or no. That's not what matters. We're looking for, can you justify it in terms of critical thinking? Then we have some calculations, and you'll notice that I've written the solutions in the same way I showed you at the midterm review session. So define your variable, figure out what its distribution is, and then figure out what you want in terms of that distribution. So we're here looking for the probability that a certain number of the observed trucks were either FedEx or UPS. If X is the number of FedEx or UPS trucks out of the ones that were observed, then the number of that number is binomial, because the trucks are independently from each delivery company, and we know how many trials there are. That's how many trucks have passed, and the probability is going to be the probability of UPS plus the probability of FedEx. So we have this binomial distribution, in this case with parameters 6 and 0.7, but your numbers will be different. And we want the probability that this is greater than or equal to 2, which we could take as 1 minus the probability it equals 0 or 1, and that gets us this number here. So this kind of format is, you don't have to use it, but it's really nice to organize your calculations. Similarly, part C, this person's interested in trucks of other shipping companies. What's the probability that they'll wait until the 6th truck passes in order to see the first truck that is neither UPS nor FedEx? So again, we define a random variable. We're going to let y equal the number of UPS or FedEx trucks before the first non-UPS, non-FedEx truck. And by that definition, y is geometric, with the probability of success being the non-FedEx, non-UPS truck. In this case was 30%. So when we do it this way, when we define y to be the number of fails before the first success, then we know it's geometric. And so the probability that we're looking for, we want the probability that they have to wait 6 trials total to observe that first success. And so that means that the number of fails before the first success is 5. So I'm sure probably a few people may have got that wrong, but you probably still got 1.5 or maybe 1 out of 2. But here again, it's very clear that the probability that the person has to wait until the 6th truck passes, or whatever it is for you, that means including that success. So the number of fails is that's -1. And D similarly as well. Actually, D and E are kind of lumped together. If D, we're looking for the probability that there are fewer than 2 trucks between a fixed amount of time. We can think about defining a new random variable to be the number of trucks within that time period, which is 4 hours. And we know that the number of events in a Poisson process over a fixed amount of time has a Poisson distribution. How do we get the parameter? Well, we have to think about what is the rate and what is the time. So the rate, we had some information at the beginning of the number of trucks in an 8-hour period. It was different for each person. But then if that number divided by 8 is the number per hour. And then we're watching this for 4 hours, so the parameter for your Poisson distribution is just that rate, lambda, times 4. And again, we want the probability that this Poisson random variable is less than 2, which is just the probability it's equal to 0 plus the probability it's equal to 1. And that gives us this number here. And then for part E, related to that, what's the probability that they'll see fewer than 2 trucks before noon and at least 2 trucks after noon? So that's now taking our 8-hour period and splitting it up into 2 hours and 2 hours. Because this is a Poisson process, we have the fact that non-overlapping periods are independent. And since they're both 4-hour periods, they have the same distribution. So we can just take the probability of that we found in part D and multiply it by 1 minus that probability, basically, to get the final answer here. And then the bonus question, this is really neat. There's a bunch of different ways to do this. You could do it with kind of like an infinite sum thing. That's a little tricky. But another cool way to do it is to sort of imagine a Poisson process only focusing on UPS trucks. And so the rate of that is going to be the proportion of trucks that are UPS times lambda. So again, both of those numbers are different for each person, but that multiplied together and then times a 1-hour period, that gives us the Poisson parameter for this particular question. And then of the probability that we have at least one UPS truck in that 1-hour period from 3 p.m. to 4 p.m. Gives us this number here. So the bonus question was tricky on purpose. It was kind of a little Easter egg. If you watched the Pokemon swag, I unintentionally gave you a hint about it there. But if you got that, congratulations. Not many people did, so you should be proud of yourself. If you didn't get it, don't sweat it. It was hard, and it's okay. If you didn't, no worries. Alrighty. So if there are questions, please let me know. What I'd like to do in the last 7 or so minutes is give you a quick outline of sort of the difference between continuous and discrete random variables. So we know that discrete random variables are a countable range, and continuous random variables have an uncountable range. So that one thing alone which is literally the definition of the two of them, that causes a lot of the other differences. So because the range is uncountable, the probability that x for a continuous random variable equals any value is going to be 0. Because if there's uncountably infinitely many things, then you can't possibly have them each have a positive probability. Because if you add up an uncountable number of positive things, you will get something much bigger than 1. And probabilities overall can't be 1. For a discrete random variable, though, of course, we have like little f of x. Oh, no, little f I said. There we go. That's equal to the probability that x is equal to little x. It can be greater than or equal to 0. Right? For certain values maybe are impossible, but anything in the range, actually if it's in the range, it's strictly greater than 0 for x in the range. But for the continuous random variable, we don't have that. If we think about the cumulative distribution function, big F of x, this is the probability that x is less than or equal to little x, and it's defined for all real x. And that is actually identical to the continuous case. That's exactly the same thing. The definition is the same of the CDF in both cases. But for the continuous random variable, we have a continuous function, whereas in the discrete case, it's going to be a step function. So over here, it's a step function. If we think about the relationship between the CDF and the probability function in the discrete case, we could get little f from big F as big F of x minus big F of x minus 1, assuming it's integer valued. But in the continuous case, we don't have a probability function. There's no discontinuities, right? Like little f in the discrete case is the size of the jumps in the CDF. But for the continuous random variable, there are no jumps in the CDF. It's a continuous function. So instead, if we're looking for how quickly something is changing, we use a derivative. That's what that is. So little f of x here, little f, thank you, word for trying to autocorrect, is the derivative of big F of x with respect to x, where that derivative exists. There could be points of non-differentiability for our big F, but mostly it's a continuous and differentiable function. So that's what they're doing. Like both little f in both cases are looking at how quickly big F is changing, but in the discrete case, it's actually the size of the jump, whereas in the continuous case, it's the slope of the line. It's the slope of the tangent line to this big F curve. So that's kind of how those two variables will relate to each other. And then, of course, if we wanted big F, it's going to be like little f of 0 plus little f of 1 plus dot, 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 plus little f of x for the discrete case. But for the continuous case, again, we are sort of adding up a whole bunch of little tiny pieces, which is integration. Oh boy, I don't know if there's a big F of x equals integral, from negative infinity, or often 0, whatever, negative to x of little f of u du. Again, I'm so sorry about the bad table here. So again, that's by the fundamental theorem of calculus. Like if little f is the derivative of big F, then big F is the integral of little f. In terms of then how we can use these functions, we haven't necessarily gotten to it yet, but here's a hint. If we want the expected value of x, it's the sum of x times f of x, right? Over all values of x in the range. So if the discrete case is a sum, what do you think the continuous case is going to be? It's going to be, spoiler alert, the integral of x f of x dx over all x, which is pretty neat. The other thing actually that's similar between the two of them is the properties of some of these functions. So like little f of x is greater than or equal to 0 and sums to 1. That's true as well for the continuous case, but little f of x is also less than or equal to 1 in the discrete case, but not in the continuous case. In the continuous case, little f of x is allowed to be bigger than 1. And that kind of blows people's minds, because like, how can a probability be bigger than 1? Well, in a continuous random variable, little f of x is not a probability. It represents kind of a relative likelihood of the probability of being near that value. So little f of x itself in the continuous case is not a probability. Again, like the higher it is, the more likely it is that the variable will be near there, but it itself does not represent a probability. We sometimes use it like a probability, like in terms of when we're calculating the expected value, it kind of plays the role of that, but it is not a probability. So I want to emphasize that here, that it can be bigger than 1. And if you want an example, if you consider the thought question 3 from week 7, that variable, if you graph its probability density function, there are points where it is bigger than 1. So it does not have to be less than 1. Similarly, properties of the CDF, actually, big f of x is non-decreasing, goes from 0 to 1, and what's the other one? I guess bounded between 0 and 1. The limit as we go to negative infinity is 0. The limit as we go to positive infinity is 1. And it's a non-decreasing function. And all of those properties are the same, exactly the same for the continuous case. It's just that it has one extra condition, that it is a continuous function, whereas in the discrete case it doesn't have to be. So that gives you a pretty good outline of some of the differences between discrete and continuous random variables. There's others as well, and there's also lots of things that are the same. So everything that we've learned about mean and variance, like the linearity of expectation, I'm going to add that to my list. E of ax plus b, ax plus b equals a e of x plus b. That is the same in both cases. Linearity of expectation still holds. Same thing for variance. The variance of ax plus b being a squared times the variance of x, that's going to hold as well. Because all of that doesn't have anything to do with whether the variable is continuous or discrete. Anything that you could prove in the discrete case using sums, you could prove it in the continuous case using the PDF. And sorry, I just noticed here, this shouldn't say sums to 1, it should say integrates to 1. There we go, so I just fixed that. But basically it's the same idea. All right, so the person who asked that, is that a good kind of overview of some of the key differences? Hopefully that was a little bit helpful. Thanks for the question, and thanks everyone who tuned in today. Have an awesome weekend. Assignment, computer-assisted assignment 2 will be posted at some point today, so it's not due for another 2 weeks, so you got lots of time, but if you want to start checking it out, you're welcome to. As promised, there is a fun question about D&D, although it's not actually D&D, it's we made up another game, and some neat questions there, and another R, a set of info about R will be posted as well. Have a great weekend, and see you next week. Bye.